Thank you. We're going to talk about recursion schemes. My name is Harold Carr. I work at Oracle Labs doing blockchain consensus research, and we use Haskell and Agda for doing our work. Recursion scheme is a pattern, and we know in functional programming we're looking for patterns all the time. And we don't have loops, so we use recursion. But there are different kinds of recursion, and this talk, it kind of goes through this. And generally, when you see a recursion scheme talk, it does two things at the same time. It shows you recursion schemes in terms of the operation of some functions, and it also shows you how to do that with any data structure. The trouble is, when you do those together for a beginner, it makes it harder. So I'm doing just a list-only version of a number of recursion schemes and mentioning the other bit later, but so it's really to focus on just the operation of the actual recursion functions. So for today we're going to do is look at some explicit recursion, what we generally write in like the first 1 or 2 chapters of a functional programming book, and then we're going to show how to factor the recursion out using a fold, and then we're going to show a whole library of a bunch of functions for folds, unfolds, folds followed by folds, etc. And then I'm going to, at the very end, talk about also factoring recursion out of data. So here's some of the ones we're going to talk about, and they're kind of known on the left side, recursion, and you basically have some data structure and you do something to it, like fold it down to one value or something. And that's known as recursion in data. And then the other one is co-recursion. And that's just like, you know, we know domains, we know codomains, we know monads, we know co-monads. It's the same idea here. They just call it co-data, meaning you start with something and it might go on forever. And co-recursion is how you deal with that. So there's nothing magic about the name co-recursion or co-data. I know when I first saw it, it like kind of scared me, but after a while you realize that there's no magic. So here's explicit recursion. And can you see the cursor is there. So I've just explicitly written, I'm going to do a sum of a bunch of, a list of x's. And they both have the same pattern, right? When you get to the empty list, you have some base value. And then the inductive case, when you have more things to look at, you say whatever the operation is, and with the front of the list, and then you recursively call that. So they're exact same pattern, and that's usually the very first thing you learn about recursion is you can use fold for that. So that same sum and using fold R is just you specify what the operator is and you specify what the base case is. And what that looks like is here's the list you have to begin with, and you just, in a certain sense, replace the cons operator, the colon, with whatever the function is. In this case, it's plus. You're plussing 1 with the result of plussing 2 with the result of plussing 3 and 0. And the same thing goes for and. And of course, they can ignore their arguments, like if you're doing length, you just do 1 plus and completely ignore whatever the actual element values is. And this is the definition of fold R. You're given an element, and you're going to, and then 2 elements, but the second one is the B, what you're turning it into. So in some case, you're turning a list of integers into a single list. And you're given the 0 element, here's the list you're turning into something, and the final value. And what it does is just calls the function you give it with the head of the list, and a recursive call to the same fold R. That is the very first recursion scheme. So we're going to now jump into a bunch of recursion schemes, and there's a whole bunch. I don't think we're going to get through all of them today, but we're going to give a pretty good try. So the first one is called catamorphism, and actually catamorphism is a fold R. If you look at there's the definition of fold R, and there's A, B to B, given a B, list of A to B, and if you look at the catamorphism, it has the exact same signature. So it's just two names for the same thing. And I've named everything Cata L. Normally it just says Cata or something, to L because this is a list-specific version. Remember that these are going to be generalized, so you can run these things on most recursive data structures. So just like we did a moment ago, and these slides are executable. I have this thing, a little routine, test routine, so I give it a name, I run the thing, and I get 6 back. So whenever I update my slides, I run the test suite for the slides, and it lets me know that 1, they compile, because this is literate Haskell, and 2, all of the things that I've written as examples actually work correctly. So we've seen catamorphism now a number of times, and you can do anything you want with it. So here I'm giving a list of strings, and I'm calling read, which read turns something into a different data type, and Haskell's going to infer that I'm going to turn it into an integer or a floating point because I'm using plus, and the B is a floating point number. So it basically turns the string into a float, adds the floats together, and returns the whole thing. So let's actually move on. Actually, this one's kind of interesting. You might see this too when you're talking about recursion schemes, is a lot of times the function that is given to the Cata L, or any recursion scheme, is called an algebra or a coalgebra. And once again, that's threw me at first because I thought there was some magic going on. So instead of calling it F, call it an algebra. And all that means is you have some data and you have some operations on that data. And in this case, like if we define filter with this algebra, it says that in the case that P is true, then I'm consing A onto something. And this is interesting because it's using currying because there's only taking one argument here. I mean, the algebra is taking one argument. So it returns this function. And the fold, when you look at this definition, this one function then will turn into A cons onto whatever this returns. So it's a little brief. And if it's P is not true, it returns ID, which means it's going to ignore the A and continue. Okay, anamorphism. And anamorphism is the word comes from meaning upwards, and I forgot to say cata means downward, and who knows who made these up and why, but in a way, you have this thing, a structure, and a catamorphism, you're taking it down to one thing. Although it's much more general than that. You can actually take something big and return something even bigger. But in general, the concept of folding is taking a structure and turning it into something else, and conceptually smaller, but it doesn't have to be. Same thing with anamorphism. You start with a seed, one little thing, and you're going to build up a structure. And that structure could be infinite. And these two definitions show that. The first definition has no stopping case. So it just says, given a B, which is the seed value, return me an A and a B. And then there's the seed value here and a list of A's. And how that works is you run the function on the seed value, and it returns whatever is going to be the value for that round of the anamorphism, and it's going to return a B prime, which is the seed for the next iteration. And so you just cons the A onto the recursive call. And this goes on forever because there's no stopping point, which in most languages you really couldn't write this. But in Haskell, because it's lazy, until you actually ask for the value, it won't continue. And I'll show you that in a moment. It's also handy sometimes not to, actually in Haskell library, it defines unfold this way. So it says a B and a maybe, the A and the B. So it's really the exact same thing, except for this A, B up here is wrapped up in a maybe. And maybe is like scale optional. That way, if you return nothing, you're done. So you don't have to rely on Haskell laziness to build just the right thing by somebody else calling and ask for it. But it's the same thing. If you run f of b and it's just a and b, it looks just like running the fb up here. But if it returns nothing, then it's done with the recursive calls. So here's a real simple way to use the anamorphism. We have a coalgebra which says when I hit 0, just return nothing, and otherwise give me an x, which is a star, and count down. So all this is doing is defining replicate, so I'm now replicating whatever I give it 4 times. Very, very simple. And you can do bigger things with it. And here's like Fibonacci, and where I'm using the ff function, which is just returning the a that was given, and returning the a, which is the answer for that round, and then the new b and this a plus b. And if you run it, and this is my test thing where it's kind of doing equational reasoning, you can see that each time it runs through, you can see what's given to the f here. Okay. And there's other examples, but I'm going to keep moving in the interest of getting through more recursion schemes. Also, doing merging lists. So, and I'm going to skip this one too because it'll take too long. Here's one that's pretty simple, and that's an infinite stream. So, given this algebra, which just says for the x, give me the x and then run f of x for the next round. So iterate is just +1, and there's the base case. And this one, once again, this is using the ANA, which doesn't have a just value. It doesn't return a stopping point. So it's relying on Haskell down here to say take 6. So I only want 6 from that infinite stream. So even though the stream's infinite, by definition here, it's not infinite until you ask for it. So if you ask for all of it, well, it would continue. If you had enough memory, it would try to do it. Okay, the next one is called a hylomorphism, and that is just a composition of an anamorphism and a catamorphism. It's first you run the anamorphism to build up some structure from a seed, and after you've built that structure, then you run the catamorphism, so it does whatever operation you want on that structure you built up. And you can see that here, the definition is you have the kata algebra and the kata 0, and then you have the ana co-algebra, the ana seed, and then the final result. So the function is just run the anamorphism and then run the catamorphism. And you always got, I'm now doing well because I've shown you fib and now I've shown you fact. So I've done the right functional programming thing. Both are here. And all this does is say, for this hylomorphism, here's the co-algebra, which says b and b minus 1. So this is going to be a list of b's, then b counting down until you get to 0, and that's nothing, and then it's going to run times on that. And there's a result. Now, why would you do that? Say, it's like an anamorphism followed by a catamorphism. The nice thing about this is both the implementation and a lot of times the compiler can be smart about hylomorphisms, and it actually won't run the whole anamorphism and then do the catamorphism. It won't build up the intermediate data structure. And you can see that. Here's the definition I already gave here, hylomorphism. Here's an alternate definition, which is something more like you'd find in the library. And that is, it still has the 0 value here for the algebra and the seed value for the co-algebra. But what it does is it runs the co-algebra one round, and when it comes back and says, okay, here is the result and here's the piece for the next round, now it takes that and it calls the algebra. So you notice it's not building an intermediate list or in this or whatever it is, and it just says, here's the algebra, and then on a recursive call to this internal function h, which then runs the coalgebra to get the next value. And that's known as fusion or deforestation. So that's another reason to use recursion schemes rather than writing your own, because somebody's probably gone to a lot of trouble to do these kind of tricks to make them more efficient. Okay, next one, paramorphism. Paramorphism is pretty much exactly like a catamorphism. It just has one more argument. Before, when we looked at catamorphism, it had an A, it didn't have this list of A, and then a B and a B. Everything else was exactly the same. So all it's saying here is that given the F, the 0, well, I call this F here, that should be algebra, given the algebra, giving a 0, and giving the input list, and then this is the final output. So you can see it just takes the input list, splits it up to the first element and then the tail of whatever is coming. And both of those pieces are given to the algebra besides the recursive call. So that can be useful, and this is a real simple example. I give the function to the paramorphism. I'm just ignoring the first argument, which is the head of the list, and I'm saying for the tail of the list at this particular moment, cons that on to the result of the recursive call. So if you call tails, you just get, of 1, 2, 3, 4, you just get successive tails of it. And that's probably a little more interesting in this one, and this one, I've needed this many, many times, where I need a sliding window in some sort of structure of exactly a number of elements. So this one just says, given the A and the tail, I cons it right back on again and say when it's less than n, return the B and be done, or otherwise take n out of this, which is saying, given this list 1 to 5, I first have the whole list, so I take the first 3 elements, then I get the next list from 2 all the way to 5, but I only take 3 elements, and then the 3, 4, 5. So paramorphism is relatively simple, and para means beside, or in parallel with. And so you can see that parallel part where you just have the element and you have another piece. So you've got 2 pieces of data, and I guess that means they're next to each other or something. Once again, who knows where these names come from? The next one is apomorphism, and that is a dual of a paramorphism. It's really just an extension of anamorphism. If you look here, here's the ana definition, and you notice it returns a maybe A and B. In the apomorphism case, it returns a maybe of the A, which is just like this A, but the B is either a left B or a list of A's. And so how that works is, let me go back to this page. This just enables you to short circuit. By short circuit means when you get to a certain point, depending on the coalgebra you give it, you can say, I don't want to iterate anymore. I want to bail out. Basically break in Java or C or whatever. So what it says in the definition is, I keep losing the cursor. I run the coalgebra. If I get a back with a left, that's just like what we had before with anamorphisms. So I cons the A onto the recursive call onto the B's that it says it wants me to continue with. If I get back an A with a right, that's the short circuiting that says, oh, okay, just take the A and the A's and done, no recursive call. And then the base case, once again, is nothing, so you give the tail into the list. So it's pretty much exactly an anamorphism, except for a way to bail out early. And here's a way to see it in action, insert element. So given this 3, I want to insert this into 1, 2, or 5. So if you look through here, it says that the apomorphism, the insert element, cons that A, this 3, onto the beginning of this list, which is the one you're searching, and then you call it, and if there's 3 elements in the list, it says if it's x is less than y, here's where the short circuiting happens. It says, okay, return the x, return the y cons onto the rest of the list, and you're done. If x is greater than y, then continue looking for where to put I in the list. And when there's only one element, or just continue, so it'll end up into the base case, which is nothing, and then you get the tail end of the list. So that one was anamorphism. Checking my time. Okay, we did that. Okay, here's one. This one is a lot. It's a zygomorphism, and it's a generalization of paramorphism. And this is a fold that depends on the result of another fold. And you can see here that the F gets a B and then returns a B. So that looks just like the catamorphism we've already seen. And then we see the G that gets the result of this F. And these B and C are the zeros, and then there's the input and output. And there is the definition. It's actually implemented with the catamorphism, but it gives the catamorphism its own function besides the user's F and G that takes the A and the BC from the from the pair here that's given in, and returns running F on A and B, and then G on A, B, and C. So we won't try to understand this in detail. The idea of this talk is just to kind of give you a flavor of the different types of recursion schemes, and then you can work on them to figure them out yourself to a certain extent. But the idea is these are very useful to go and start using. So here is a zygomorphism in action. And this is pretty simple. All it's doing is given, in this example, given this list, 1 through 6, I want to negate every other element. So that's pretty straightforward. So what I do is the first function, I'm ignoring the first element and looking at the second one, and it's a Boolean, which is, here's the base Boolean, false. And I just flip it each time, so it turns false and true, false and true. And then the second function is given that B, and I'm just calling this auxiliary function I defined called PM for whatever reason. And I say if B, then return a negative A or just a regular A, and cons that onto the C. And so you can see that it does that. There's a little trick here, though, or subtlety, which notice it starts out saying, okay, false. And remember, false says to give me a negative A. Well, it's true. If it's true, give me a negative A. But what I'm getting back is -1 here. Why did I get a -1 there when I said false to it as the base value? And the reason that is because this actually builds up. It traverses from the front to the back, but it builds up from the base cases from the tail forward. And you can see that easiest because I say when I reach the end of this list, this is my base case. And normally this would be an empty list. But I stuck a 45 here, by the way, 45. And so you'd see it end up here at the end. And the same thing happens. This initial false is actually applied to this 6. So that's why it's not a -6. And then it flips it, and then it's given to the next number, and it kind of goes backwards through the list in terms of how it flows. And that can be a little confusing when you first use this. And there are versions of all of these things that'll do it. You know, you've heard fold right, and there's fold left. So you can do it from the left, so it really will have those values start at the left side. All of these examples here are all basically going from the right. Okay, histomorphism. And I was so happy the first time I actually used this in production code. But I did it after I gave the talk, so I knew it existed. Otherwise, I would have probably wrote the histomorphism myself in probably a poor version of it. So it was nice to know that it existed. And this one, you're given access to values that were already computed before. And although the before, once again, is a little weird because it's working from the right end up. So even though it's histomorphism, the histories feels a little bit like the future. And here's what this looks like. You have a data type called history, which with two constructors, end of B, which is just your base case again. So when you get to the end of the structure that you're traversing, that's the value you're going to use. Otherwise, you're going to do a step, and this is the step value, and this is the B value, and it's wrapping up the history that already has happened. So this history function is given a function, which is the one you're going to use, which is given an A, return a history, and a history of A and B, return the B. So here's your initial value, or your base case value. Here's the list you're going to traverse, and then here's the final history. And once again, this is done by using a catamorphism, which says, given the A in the history, here's wrap it up in a step with running your function you're given over those values. So when you look at this thing, it's not trying to do anything, but just show you the operation of a history, which I'm just saying for that function I'm giving it, just return the A as it's given directly, and then show me what the history looks like. And do that with the base case of a 0 and a string on the list 1, 2, and 3. So the first time, the outer wrapping of this whole thing is just step 1, and the value it has is that A, same thing. And then you can see all the other ones. I let it run off to the right of the screen, but it's essentially the same thing. To see that how it gets useful, I'm defining these helper functions, val h, which means giving you the value out of a history object. So in the step case, it's the B, the middle argument. In the end case, it's the only thing it has, the B. And previous just says, given a history, give me the previous history. If you're already at the end, you just return what you gave it, because there's no previous history. And if you're in a step, you grab the history. And that makes it useful to define Fibonacci, yet again. So with Fibonacci, the F is just, given a history, add the value of the history to the previous history. And how that looks is when you run this function, it goes all the way to the end here, and that's the initial value you gave it, 1. And then this step will have a value of 2, and when you add those together, it becomes 3, and then 3 and 2, 5, and it goes up this way. So when you're at each iteration, it has access to all these other values. So that's where the useful history comes in. And I can't remember now why I needed to use this. It was in some sort of crypto thing that I was doing, but it turned out to be very useful. So that was histomorphism, and this one's futo, how do you say it? Futo? I guess futomorphism. And this allows you access to future values. So this one I'm not going to go through in a lot of details, other than to say, well, let's walk through it a bit. The function you give it yourself is, you're given an A value, it returns a maybe of a B, and then a list of Bs, and then a maybe of A. So it's a lot going on there. So to run this, the future comes in right down here. And that's when you run this function, it actually runs f of a here, but then it says, depending on the value back, that m of a, this may be a right here, if that is a just a prime, it will run the future morphism with that same function here and give you back the future b's, and that's the ones then that are put at the back of here. Otherwise, nothing if you actually don't take advantage of that. So this one, I haven't figured out a good use case other than this example. I'm sure there is, and I haven't taken the time to look up in the literature interesting use cases. I think it's used in dynamic programming. But just to show it in operation, this just says an exchange. And all the function that I'm giving it says for the function just says for all the x's I've given, take the head of the tail, and that's going to be the a. And so I'm actually getting the second element of the list, essentially. I should have put second there. It'd be easier to read. And then the head here, which is the first element, and then the rest of the tail from the third element on. So you can see all that is doing is just exchanging every two elements, every two pairs of things in a list. So given 10 minutes, okay. So it's just exchanging, and it handles edge cases right, because I notice in this one, if I'm only taking 9, I exchange, but it drops the 9 off. So you always want to make sure your edge cases. Okay, perfect timing. He just told me I have 10 minutes, and so that's all the recursion schemes, and that's the functions themselves and some of their operation. As I said earlier, you can also refactor recursion out of data. And there's two main ways to do that in Haskell. And one, here is a tree data structure, and it has a leaf and then 2 branches. And you just say deriving foldable. And what that does is builds behind the scene. It allows your functions to be able to use like fold_r. So when I build this example tree, which is just 1, 2, 3, 4, a balanced tree, and this tree is not a balanced tree, I'm just built a balanced example. And then I run ++ on these strings, it concatenates them all together, 1, 2, 3, 4. So that was done for you automatically. You didn't have to do a thing. So that's one way to factor recursion out of your data structures, is derive foldable, also derive traversable. But the one way that you'll see when you see other talks and blogs and stuff on recursion schemes, and this is the part that I think confuses beginners, I know it confused me on recursion schemes, is you define your tree, which remember looks the same thing. I have a tree of A, and they have a leaf with that value, or a binary tree, which just of those the same type. So this one says the same thing. I have a leaf of A, and here's that same leaf of A, or a binary tree. But notice there's this extra parameter, which I've labeled R just to mean recursive. And then I derive functor, and I'm not going to try to explain this. It's just, this is the part that just to know it exists, and you can use it. So you add a parameter. You put that parameter wherever there would have been a recursion in your data structure, and there's the recursion here, bin of a tree of A, which is the type. So where that type is, I've replaced it with R. So, and then derive functor. Then I wrap this up, so this type with a fix. And fix is kind of like a general recursion type. It factors the recursion out of your data type. Because if you said you had a list of L tree F, and then you wanted to do a bunch of those together, you would have to explicitly have a different type for every level of your tree. With fix, you actually just call it fix, and that is hiding the recursion in the definition of fix, which I definitely won't show you because it's completely inscrutable to beginners. And actually, when I look at it still seems that, actually, what I said earlier, there's no magic, but their fix might be magic. So, and then I have some smart constructors, because when you actually build one of these things, each time you want to create a leaf, you really need to wrap it up in that fix. And you don't want to be doing that all through your code. So with smart constructors, I can now say pretty much what I said before, except for having uppercase bin and leaf. I now have the same thing down here, lowercase. But other than that, it's the exact same thing, and it conceptually builds the exact same recursive structure, but it's using fix to handle the recursion. Now, the real definition of kata in recursion scheme libraries is built so it'll work on any data type that is using this fixed point operator. And how that works is somewhat, the main piece is this unfix here. So every time it goes through a level of recursion, it takes off one of those fix wrappers, and that's what unfix does. And once it's done that, it's given, your algebra is actually given that base data type. So if I have a leaf of A and I'm doing sum, which this is the same one I was doing before, I'm calling it sum, but I'm really concatenating, so I should have called concat. So in the case it's a leaf, I just return the value. If it's a two trees, I just concatenate the left and the right together. Notice at this point, I don't even have to think about the recursion in the system, because all this unfix and the kata is handling all of the recursion, and all I have to think about is the values themselves at that level. And it operates the exact same way. So yeah, that is it. So the idea is use recursion schemes. If you want to know more, this to me is the very best recursion scheme talk. But it immediately jumps into using fix and unfix. So but it's a really good presentation, and I stole a lot from it. There's also the kind of canonical references, this bananas, lenses, and envelopes and barbed wire, and that's one to read. And then these slides are on this GitHub page. So thank you.